Hello and welcome to my channel. This is the third question of chapter 2, and in this video we'll be going over midpoint convexity and see under what condition midpoint convexity implies convexity of the set. So midpoint convexity is saying that when we have 2 points A and B in set C, then we find the average of these two, and the average is back in set C. Now the question is, does midpoint convexity imply convexity? And the answer is no. However, we will see that under a mild condition, and that mild condition is closedness of a set. And if we have that closeness of the set, we are going to have convexity. So let me show you what I mean. So as I explained, the set C is said to be midpoint convex when 2 points A and B, which are in set C. Now consider these 2 points A and B in set C. Set C is all the points here. Midpoint of these two is the average of these two, which is going to be here. As you can see, that average is also in set C, therefore we call this midpoint convex. Obviously, convexity implies midpoint convexity, but we need to show that. We know a set is called convex if for any pairs of x and y in C and any lambda in the closed interval between 0 and 1, we have lambda times x plus 1 minus lambda times y in C. Just because this is always true, just let lambda be 1/2. Once we have lambda 1/2, then we have lambda 1/2 times x, 1 minus 1/2 times y, which is x plus y over 2, and that point is in C. But the problem is that the reverse is not true, and we cannot conclude the other way around because midpoint convexity does not imply convexity. To see that, I have a counterexample, and that counterexample is all rational numbers in closed interval between 0 and 1. This set is midpoint convex. Why? Because if you take any two rational numbers x and y and then add them and then divide it by 2, then you're going to get a rational number. So this set is obviously midpoint convex. However, this set is not convex. Why? Because for convexity, we need to have for any lambda between 0 and 1, we should have lambda times x plus 1 minus lambda times y has to be in C, but this is not true. Why? Just let lambda be root 2 over 2, which is between 0 and 1. This is roughly 0.7, and let x be a rational number and a rational number. So if we let lambda be 1 over root 2 over 2 times 1/4 and 1 minus lambda over 2, 1 minus root 2 over 2 times 1/3, then we're going to get this number, which is not a rational number. Therefore, a midpoint convexity does not imply convexity. But if we add some more conditions on the set C, then we will see that the other way around is also true, and that mild condition is the closeness of a set of set. So in next slide, which is this slide, I will be showing that for a closed set, we will have that condition to be satisfied. So we have a set that has the property of midpoint convexity, and the set C is closed. But let me just remind you what a closed set C is. A closed set C is a set that contains all limit points of any sequence that is in the set C. So what I mean by that, let's say you have a set C, and this set C, we take a sequence like this, and that sequence is converging to this point. And as you can see, all the points are in C. Therefore, in order to have the set to be closed, we need to have the limit point, which is here, has to be in set C. But that might not be a very good example. I have a very intuitive example. Just consider a closed set between 0 and 1. This is a closed set. But this one is not a closed set because we have open interval on the left side. It is not closed, and how can we use that definition I just mentioned to show it is not closed? Just take a sequence an as 1 over n. The limit point of this sequence is 0 because limit of 1 over n as n approaches infinity, it is 0. 0 is not in this set, so this set is not closed. So we need a closed set. Now, our goal is to show that a set that has a midpoint convexity property and also it is closed, it has to be a convex set. So we need to take two arbitrary points x and y in any lambda and show that this point is in C. But before going to the detail of the proof, let me show you how this works pictorially. Given a lambda and 2 points x and y, we want to show that z, which is a convex combination of x and y, is in C. But what we can do is to proof is that to look at the set C. So we have a set C right here. This set C is closed and midpoint convex. So pick 2 point x here and y here. The only operation that I am allowed because of midpoint convexity to preserve points in set C is just the average. So I will take the average of x and y. So that would be z1 over here. Now I should check z1 if z1 is closer to y or x. In this case, z1 is closer to x, therefore I will add x and take the average, which is this point, and I will end up with z2 right here. But here, z1 was x plus y over 2, and if you expand that out, you're going to get x over 2 plus x over 4 plus y over 2. Now we need to do this process again by checking that if if z is closer to z1 or z2, in this case it is closer to z2, therefore I am going to add z2, not x, to z1. And once I do this, I should have x plus y over 2, and then z2 was this guy. If you expand this out, because we have 2 and 2 here, we get x over 4, and here we have 2 and 2 and x, we have x over 4 here, and here we have 2, 2, 2, so we have x over 8, and for y we have y over 4 because I have these two, and y over 8. Now you can see we have x over 2, x plus x over 8. Remember that we started with a coefficient of x as 1/2 here, and then I modified that to 1/2 and then 1/4, and then I realized the formula modified that for me to 1/2 and 1/8. So this is z3, and let's look at z3 in detail. So z3 is this guy, and if I just factor out coefficients of x, I'm going to have 1 over 2, 1 over 8 times x, and this is called lambda. I will call this lambda 3, and this is also 1 over 1 minus lambda 3, and the sum of the all coefficients, no matter what index you use here, is going to be 1. So let's try to characterize these numbers here. So it is 1 times 1 over 2 to the 1 plus 0 times 1 over 2 to the second plus 1 times 1 over 2 to the third. And if I keep this, if I keep doing this k times, I will get something like this: c1 times 1 over 2 to the 1, c2 1 over 2 to the second, and so on. Ck's are 0 or 1. And that definite, and at the end, this lambda k will converge to the actual lambda we have. Uh, uh, so after k steps, we will find the closest midpoint to the point that we have. So zk would be lambda k times x plus lambda 1 minus times 1 minus lambda k times y, which is in C, because we realize that all the operations I have done so far in order to get zk was just the average, and average may keep all the points in set C. And then we know that sequence of zk is a convergent sequence. Because it is a convergent sequence, it has a limit point, and that limit point is a limit point z. And since C is closed, this is the place where closedness of set C comes into the picture, and we can use that to conclude the proof. So C is closed, therefore C contains all the limit points here, and therefore if we just take the limit of zk, we are going to take the limit of the convex combination, and then we realize that lambda k is going to converge to lambda, therefore we get z. And because this is a limit point, z is in C, and we just showed that z is in C, and our goal was to show z is in C, therefore set C is convex. And that concludes the proof. Thank you for watching me, and I hope you have enjoyed this video. Please do not forget to hit the like button and subscribe to my channel in order to let me know that you are enjoying these videos, and I can provide you more videos on these solutions. Have a good day.